We'll now look at an example of a two-sample proportions problem, and this is an example. A survey was carried out of senior citizens' attitudes and desires about retailing. For a random sample of 232 shoppers aged 65 or older, 25.0% indicated a desire for more courteous, dignified, and patient treatment of older customers. In a random sample of 106 shoppers aged 55 through 64, only 19.8% indicated that this was their primary desire. Is there a significant difference between the proportions in both age groups? Now for 5%. So we have our two groups, over 65 and the group just under that, and we have the proportions that had this as their primary desire for the two groups. So let's write down our sample information. So group 1 will be 65 or older. Sample size there is 232. The P1 hat is given to us directly, which we'll find out is not always the most helpful. And that was 25% or 0.25. The other age group was 55 through 64. We'll call that group 2. N2 of 106 and P hat 2 of 19.8% or 0.198. Alright, so the question was, is there a significant difference? The word significant is a weak word, so we won't use that to describe the hypotheses, but difference is the question, with an alpha of 5%. Alright, difference is a two-tail situation. Alright, we don't care which way it is different, up or down, so this is two-tail. So we have no choice about our hypotheses. Null hypothesis will be that P1 is equal to P2 and the alternate P1 not equal to P2. And of course the alternate is where the two proportions are different. In the null, they're not different, and we can say that, or we can say the same. Actually, when it comes down to our interpretations, especially using the word significant or insignificant, not different will help. Okay, so now we need to draw our normal distribution. Remember, this is a proportions problem, and all our proportions problems will be large and using the Z. So we have our Z distribution, middle is 0, and this is a two-tail test with a total alpha of 5%, and so in each tail we have half of the 5% or 2.5%. Let's go to the t-tables, find the value, the critical value. Alright, remember the last row of the t-distribution is for the z. We want 2.5% of the tail, and it's the old favorite value of 1.96. So our critical values on this distribution are plus and minus, or positive and negative 1.96. So our decision rule will follow this. If our calculated z-value is between plus and minus 1.96, do not reject the null. It's possible that proportions are not different. We will use the words insignificant, but in any case, we'll see that in a second. If our z-calc is beyond plus or minus 1.96, that is below 1.96 above, plus 1.96, it is likely the two proportions are different. Okay, so let's write down our decision rule. But as I sort of pointed out, let's do the interpretations this time with the word significant. Not that it matters in the long run, but which way you do it, of course. But we'll be using the word significant a lot, and it's time to get used to it. If we're doing z-calcs now, if z-calc is between positive and negative 1.96, right, two values too close together, it's possible they're the same, so do not reject the null. And our interpretations now, we can say there is an insignificant, statistically insignificant difference between the two groups. Insignificant means just like possible, they're the same. You can't tell if they're different or not. They're too close together. Alternatively, if z-calc is not between positive and negative 1.96, then we're out in the tails. It's too far. The two values are too far away from each other. We'll reject the null as unlikely, and in its place accept the alternate. And the interpretation again using significant, there is a significant or statistically significant difference between the two groups. Now if we go with the alternate, we have positive information.